the next two talks, in addition to being a professor at the University of Waterloo and helping to run this thing, this workshop, I'm also a judge on the AI X Prize, which has been happening for the last couple of years. They've whittled it down from 150 teams from around the world that are working on AI for good problems in response for on the goal of getting a few $1 million prize. And they've whittled down now to 20 teams over every year. There's kind of like checkpoints and awards. And just this week in Montreal, we had a milestone checkpoint of the top 10 teams of the remaining 20. And we selected 2 of those teams to come here and give a short accepted talks. And the first one today is going to be from Zzapp.
Hello everyone, my name is Arbel, and I'll be talking about how Zzapp is using artificial intelligence to fight malaria and towards malaria elimination. So malaria used to be everywhere, all over the globe. Today, it's been eliminated in many countries, and 90% of the malaria burden is now in sub-Saharan Africa. Still, over a third of the world's population is at risk of contracting malaria. And every year, there's 300 million new cases reported, leading to over 450,000 deaths. And in addition to being fatal, people who get sick with malaria can't go to work, can't go to school, and it also leads to a loss in development, in addition to the actual cost of malaria interventions. The WHO set a goal for 2030 to eradicate malaria in over 35 countries. But recently, this year, after a decade where each year the reduction in malaria has been smaller and smaller, this year we're not seeing any reduction in the prevalence of malaria. The methods are becoming less and less effective. What methods are there? Most of the methods target the actual mosquitoes that transmit the disease, the Anopheles mosquitoes. Methods such as spraying the inside walls of a house so that when a mosquito lands on it before or after they bite, she bites, she dies and cannot transmit the disease. There's bed nets that you sleep under. They're treated with insecticides. Spraying of water bodies that is effective against the mosquito larvae. They need water to develop. And those 3 target the actual mosquitoes. There's one method that targets the actual Plasmodium parasite, which is distribution of antimalarial drugs on a large scale to an entire community at once. The problem is that the effectiveness of each of these methods in a given location depends on many factors. For example, the method of spraying water bodies in areas that are very sparsely populated, or areas that are where there's a lot of precipitation or swampy areas, there's too many water sources or water bodies per person for this method to be cost effective. Another example is the ratio between indoor biting mosquitoes and outdoor biting mosquitoes. Methods like bed nets and house spraying are not effective if outdoor biting mosquitoes are more prevalent. And actually there's many interactions and many factors that make it difficult to select an optimal intervention for a given location. So far the solution has been blanket interventions, which means taking one of the methods, or 2 of the methods that are most commonly used, and implementing them over large areas, which leads to an inefficient use of resources and basically using interventions that are ineffective in certain areas anyway, because of the lack of planning that's offered. So our solution is an AI-enhanced planning tool that will basically assume the role of the malaria expert in deciding what interventions should be performed where. And it does it by looking at individual communities, offering individual communities different interventions. So this is an example of what a recommendation might look like. For example, a big city where there's fewer water sources per person, larviciding may be more effective, which is treating the water bodies. But in smaller areas or in areas that are far from water, there may be different interventions that would be recommended. So I want to show an example of how we're using artificial intelligence to develop this planning tool. So I'll give the example of the spatial factor. How we know, we could, of course, so this is a demonstration of a village, a simplified map of a village where in brown you see the houses and in blue you see the water bodies. And of course, the best method would be to spray all of the houses and spray all of the breeding sites, the larval habitats. And that would, of course, get the most reduction in malaria. But the problem is that there's limited budgets, and you have to decide how you're going to maximize your budget in a given area. So what we can do is we can take advantage of the synergistic effect between different methods and spray some of the houses, spray some of the breeding sites, and get a better result. So this is an example of what it would look like, where in green are treated houses, and in orange are treated breeding larval habitats. So these representative maps of villages we take and we use to train a convolutional neural network that basically enables us to predict how what the mosquito population would behave given a certain intervention. By knowing the mosquito population, we also know if the intervention is going to be sufficient for malaria elimination, and also the duration that it would take to reach malaria elimination in that location. Given the fact that there are many possible combinations, we can spray any number of houses, any number of water bodies, we use simulated annealing to find the optimal solution, the optimal combination. When we evaluated the algorithm and the recommendations, we used simulated data to show that the recommendations made by the algorithm perform better than both random strategies, which is just spray randomly given your budget, and also compared to strategies informed by research, such as spraying houses that are around water bodies, because that's where the more mosquitoes would be, or spraying around the border of the village, which is actually something that came up when we were looking at the results that were being recommended by the algorithm. Right, so this is using simulated data, but we also would like to get real data. And actually our first product was a mobile app. It's a GPS-based mobile app, and it's used to facilitate the implementation of interventions in the field. So a big problem was the thoroughness of the interventions. Employees would be given a village to scan for water sources, and 40% of the water bodies would be missed. Or they would need to spray houses, and they wouldn't know which houses have already been sprayed, which houses need to be sprayed. So this app helps them, it guides them around the village, lets them know what houses need to be treated, what areas they've already scanned. As you can see in the picture on the right, it kind of marks where they've been and shows them where they need to go to continue scanning. And we tested this app in Ghana this May. And we were able to show that workers guided by the app found 28% more of the larval habitats compared to the methods that were being used before. So data that we collect using this app will also allow us to train our model further, our neural network further. We've already implemented the app in Ghana and in Kenya, and we're implementing it next year in Zanzibar. Also trying to collaborate with the South African Ministry of Health and the Senegalese Ministry of Health, and that's us in Ghana. And we're trying to get various sites so that we have different kinds of data, because different places are using different interventions, and we're not really telling them what to use yet. We're kind of gathering information first about what's happening, what's being used, and how effective it is by monitoring the mosquito population using traps first, so that we can train our model and then move on to actually testing if the model works in real life by giving recommendations that perform better. Another project that we're doing next year in Zanzibar is incorporating drones to scan, because they can scan faster than people. as well as satellite imagery to identify the areas that we should be focusing on. We're kind of incorporating our technology there. And this specific project was supported by the Bill and Melinda Gates Foundation, which deals mostly with malaria. This is us in the field, locating larval habitats, which hopefully we'll use to train our algorithm and be able to inform malaria elimination campaigns. I think there's time for questions, right? Yes? So if there are any questions.
You finished early. It's not supposed to happen. Great. Does anyone have a question for them?
I will say first that I'm not one of the programmers on this. I'm more on the implementation side, so I'm not sure if I'm going to be able to answer all the technical questions, but I'll try to the best of my knowledge.
Do you have one? Go ahead.
Brilliant. Hi there. Thanks. How would you compare the models that you're developing with some of the other modeling work going on in mechanistic simulation models, for example?
Sorry, could you repeat that?
How would you compare your machine learning models with some of the other work going on in more statistical mechanistic simulation models for malaria interventions?
Okay, so basically, a lot of the things we're doing have to do with spatial information, so it's very useful for us to know, to be able to tell from satellite imagery things about the intervention area. So we're trying to incorporate some machine vision into our so far we've been using the app. So the app kind of helps you map out the village in addition to satellite imagery with manual tagging. So we're looking into incorporating machine vision into that. And so we're using convolutional neural networks for this specific purpose, but data that is more to do with climate and precipitation, things like that could be, we might be looking at differently. So, yeah. If that answers your question.
Great. No, no one has a question.
So, very interesting work. I wanted to ask if it would make sense to have in your baseline whereby you just give the smartphones with some, very simple baseline to see whether the impact was based on the smartphone or your machine learning based guidance.
Right. So the first step would be the baseline. The first, we're not going to be we're going to be using the data to train the algorithm, but the first step is going to be the baseline information. And companies will be using the mobile app for the benefit of increasing the coverage of the interventions. It's separate from the planning stage. So the planning stage is an additional product that we're kind of making use of the data that we collect using the mobile app that on its own has a lot of value to these campaigns to also provide additional value.
Great. Okay, let's thank the speaker again.
Thank you very much for listening.